So finally, the training is finished. So we can see this loss got changed from 0.45 something to basically very less, like 4.5 to the power 10, 0.5 minus 5. So we have, it's about 6 decimal places, or it is 6 decimal places in here. So, or 5 decimal places. So it's not bad error. So we can see here, or it's not, it's a significant change in loss. We can see from over up there to here. So now what we need to do is to evaluate our function. So evaluate is our training is good or not. To do so, we need to a reference point, and the reference point will be basically an actual function, an actual function that can be integrated analytically. That is, we have exact solution, and we will use this to refer to it or compare it between the analytical solution, the exact solution, with our neural network solution. So we're not even going to compare numerical. But first, let's do one thing. Like we need to plot plt dot plot the loss, train losses. This is a very simple problem, so it should even converge much before. Like you have 250 was sufficient. Very small problem. So this is, all of this is just not really needed. So I'm sorry if you waited long time, but yeah, just if you saw it before, just change this epoch number in here from 2000 maybe 200 and see the results. Most likely you will get a good result. So the final thing is, let's evaluate the actual solution quality. So we start by first making a function. This we call it my function. My function equals, we have a lambda function, which will be np dot cosine 5 x. So this is my function, or the function is cosine 5x. So x will change from 0 to 1, and we will have the cosine of 5x is going to be applied. Of course, this is how it works, is we have here x, we will apply x, which we already have from 0 to 1, the 100 points. And here for x, we apply this one, and this is going to be my function. So this is basically what it means. So the integration of this function, we write it analytically. Of course, we lambda will be 1 over 5 multiplied np dot sine 5x. This is the integration of this function. Now what we need to do is u underscore t equals my function. We just populate this with the actual x, and s underscore t is going to be the integration, this one, and we will pass x. If we have a problem, integration, I think it seems no problem. Sorry. Oh, maybe 5. Sorry. We have here double points. We have to put double points, not equal. Now it's good. So you want to see ut, it will be this way. If you want to see, of course, the shape, as we always do, and we can actually see the other shape, which is also ST. So we have 100 points, and these are the name of them. These are the values of them. Now, what we need to do is we need to enter UT, which is a cosine function, into basically the neural network and see the results. So to do so, we need to change the model from training. You remember here we put it in PyTorch, we put model.train. It's in the training mode to the evaluation mode. So to do so, we write evaluate, and now it's in the evaluation mode. And then we need to change this UT to tensor. Tensor equals basically torch dot tensor, and then we pass on the t, the first this value, and dy d type. Data type will be torch dot float 32. So that's for UT, but actually we need to unsqueeze this. Or okay, let's see how it looks. This one, if it's not unsqueezed, and here we just put it dot, maybe I'm covering the thing to become like this, dot unsqueeze in the zero direction, and let's see how it looks. But before that, let's also do another thing. Now this is UT. We need the x, because the input for the function is going to be UT, the whole function, and we will need x. We need to evaluate for the whole x points. So to do so, we have x tensor torch dot tensor, and then we basically the same thing, but just we need to just here we have to have x and data type 32, no problem. Squeeze one, and I will explain now what does it mean, as I promised before. So here is put the tensor. I think we're ready, but just I want to show something. Or okay, I will just print it, and later I will show. So the first thing is here is we will take UT, and if we looked at what kind of function here, we will see that it's only a parenthesis with all of them have numbers, a sequence. So this will be, I will show basically the shape of it. utensor dot shape, and actually we need to see the other one after unsqueezing it, and the last one also after unsqueezing it. So it is only 100. It has a 100. It will have a one row, and it's only gonna have 100 values. This is not the shape we want. The shape we want will look like this: 100 points and one data type. Of course, we enter into one, but the actual correct way is to do it is we enter this one into here we will have or sorry, this is only one data point, but we can say like maybe it's also a good way if to do it is to put it here 100. It's also gonna work. The thing is, this one, when you unsqueeze it, become from this shape, and then it will have one like basically one parenthesis more. Why we need that? Because, as we said, the evaluation of our DeepONets is we need to give the whole sequence, which we're doing here, but for every step or for every data point. So this has to go basically every time we compute the function or the value of that function at a specific location, we need to have this sequence to be inputted into the system. So this is what we can see here. 1 means data point 1, and this is 100. In the model accept, or the model will accept, we will add just one time, and it will consider it, it will keep repeating it. But because it will not change, so you will take it as default. But basically, it's also okay to put it 100 points, and every 1 point, every data point will have a 100 data, 100 basically the whole sequence. Now, this is one thing. The other thing is we have here all of this thing is the X will, or sorry, the actual yeah, this is the X, no problem. This is the sorry, this is the U here, and it is corresponding here in after unsqueezing it, as we explained. Now this one is corresponds to the X tensor, and when we unsqueeze it with 1, it will basically look like this. The direction, although this syntax and this syntax is the same, the only difference is this, the squeezing, unsqueezing direction. This one we wanted to squeeze in this direction, in the arrow, in the row direction, but the squeeze one is going to squeeze them in the column direction. So this is why when we have well, if you want to print it, like we can actually print x dot shape and print x, it will basically, this is one is similar to this one, but it's not tensor. Maybe I can write it later tensor, but anyway, it's just 100 points, only a numpy array of 100 points. But when we change it to tensor and unsqueeze it, it will look like this. And what does it mean? It means that you want the integration at point 0, you want the integration at point 0 point something, and you keep asking for the integration in the all points. Every time this has to go into the neural network, it will ask for the corresponding answer. It's very interesting. This is how it works. So so this is how it's going to be calculated. So the last thing is we need to pass them through the network. Maybe these like we don't need these. It's just for kind of inspection purposes. So you can just get them out of the way, and we can just take these. And now we need to evaluate this thing. And in order to evaluate it, we write well, P, let's say, model or solution, whatever you want to call it, U tensor, and the X tensor. And shift enter. So we can see the value of P is here, but make sure that, or okay, we can write it here, just P, but we will basically remove it. This is a tensor. We don't want a tensor. We need a numpy. So P equals P dot detach dot numpy. And now we can see a nice numpy arrow that we will plot. So here we have a numpy arrow that we made. So the last thing is plot. We need plot everything. plt dot plot. We put x and yeah, UT. This is the UT here, this one. And this is going to be labeled. It's important, this step, because we need to know which is which graph is which. And this is the function. And PLT, maybe it's a bit small, dot plot. And we do the same, but this is what is going to be here, is going to be the ST, um, the exact solution of this integration. Now here, integration analytical means by hand solution, and we need to do the other one, which is P, this numpy array we talked about. Here going to be integration like deep neural network model, and we just make sure it's right. Dot legend shift enter. So we can see here, this is the function, this is the what is this, the sine, I think, the cosine, sorry, not the sine. Sine should start from 0. So the cosine, this is the cosine, and we can see it here. And the integration, analytical integration, this one in orange is this one. And the integration in deep neural network, you can see, is quite following very well. Maybe not as smooth as the other one. We can see a little bit wiggly here, but it's good. It's good. That means we are integrating a function that we never saw before, most likely, because our data is just generated randomly. So it's quite interesting. So the last thing is we will do is we change the the actual function, but of course we don't need to rewrite everything. Everything is kind of there, or it is there. So here is numpy cosine with multiplied. So this is a little bit more complex function, sine of x, and this is, you can see how they integrate this thing. It's quite interesting, and it is sine x, and all will be squared. So just you can search about how cosine sine is integrated. It's interesting how they manipulate the data to make it work. So here np sine x, like manipulation, analytical manipulation. So here this is the cosine sine function, and the integration is this one. What else we need? We need, well, we will copy paste everything. So this is, we don't need evaluation, it's already evaluation. But anyway, just make sure, like, you can just change here any function you want. And model eval, these going to be the same. So anytime you just want to change just or integrate anything, you just change these two equations, or more this one. So here we don't need actually this one, this demonstration thing. And here we just take the plotting thing and we plot. So the function looks like the blue one, this one, like this one, this, and the integration, analytical integration, you can see it here. So it's quite smooth, and the integration using deep neural network is the green one. So you can see it here, very close to each other, and definitely this operator, we can claim that it works. Now other tests you can do, or more modification, you increase the training data to include different um, kind of broad range of from 0 to 1. You change this also the make it a little bit, what if there is a function that is a little bit sharp or something, you have to also consider. So the making a 100% general deep neural network is not so easy. You need a data that actually take into consideration what you might face in the evaluation in order to get a good result. So, however, but this is shows how we can do a deep neural operator integrator, and hopefully we continue with getting into a bit more complex um, um, equations.